We all know that a rotational body of rotation remains in its axial direction. This property is already used in many ways in technology, but we don't know why, with what force and how strong this force should be, and how does it work at all. In previous physics, this movement is described with an intrinsic angular momentum L. For a rotational body with moment of inertia J, the intrinsic angular momentum is as follows. This is actually just a mathematical description that cannot solve this problem. We can also imagine that a rotating body remains at its speed of rotation, like a running body at its running speed. To investigate this movement, we take a homogeneous disk as an example, which rotates around its axis with angular velocity omega. If we consider an arbitrary mass point P in the disk with radius r, the inertial force of this point is the same. With this inertial force, the point remains in its tangential speed against the acting force F, for example, which forces this speed to change. To change the speed of rotation, this force F corresponds to a torque M. Contrary to this inertial force also corresponds to a torque in relation to the x-axis, which we call inertial torque and which we draw with this symbol. And the inertial torque of the point is the product of the point inertial force and the distance r. The total inertial torque of this disk, intrinsic inertia torque, is the sum of all point inertial torques and can be calculated as follows. It is no coincidence that this coefficient 1/2 fits the usual moment of inertia for disk J. It goes without saying that the moment of inertia J is generally valid for all rotational bodies in application of the inertial torque. Therefore, the inertial torque for all rotational bodies with the angular velocity omega can be represented as follows. Compare the intrinsic inertial torque with the intrinsic angular momentum. And the orbital inertial torque with the orbital angular momentum. Analogous to a moving body, which has the inertial force with which it defends its running speed, a rotational body has the inertial torque with which the body remains at its speed of rotation. The physical meaning of the inertial torque is: if a rotational body is accelerated to rotation by a torque m, its speed of rotation is limited to a maximum. Conversely, if you want to accelerate or to break a body rotated with omega further, you need a torque m that must be greater than the inertial torque of the body. The moment of inertia can also be drawn as a vector like the torque vector with the right-hand rule, in which the curved forefingers only show the direction of rotation, but not the direction of force as in the case of torque vector. Because the inertial torque insists on its speed against both driving and braking force. So it works both ways. Because every point mass in a rotating body also has inertial force, which opposes the Earth's gravity. Then the whole body also opposes the gravitational pull of the Earth more or less. For this we take another example like the following. If a body moves in the sky with a speed of v, as I said, it has an inertial force with which the Earth's gravity is more or less balanced. When the speed increases to approximate 7.9 km/s, the inertial acceleration increases to 9.81. So the Earth's gravity is completely balanced, regardless of the direction in which it flies and in which form it moves. That is, even if the body is circling in the sky at this speed. Similarly, a ring-shaped body can withdraw the Earth's gravitational pull when it rotates at a speed of 7.9 km/s. Even a rotational body of rotation, which is considered to be a body made up of many rings, can completely evade the force of gravity if it rotates fast enough. To evade Earth's gravity, the total inertia of the body must be equal to the gravitational force, so we have the following equation. This results in the speed of rotation at the outer edge of the disk. So if a disk rotates at a speed on the outer edge of 11.2 km/s, it can float in the sky like a UFO. How a rotational body of rotation remains in its axial direction is explained in the next video. Thank you very much for your attention. See you next time.